Good morning. So let's start our second day. And the first talk of the day will be given by Dr. James Jenkins.
Okay, thank you. Okay, so today, well, thanks for coming so early in the morning and making it here, bright-eyed, bushy-tailed. So today, I'm going to talk a little bit about some of the statistical properties of exoplanets that we've learned from large surveys. And like I said yesterday, over the past 20 years, we've been basically studying essentially the gas giant population and now just moving into the Neptunes and the super-Earths, trying to push towards the exo-Earths. So from yesterday, we went through the observational methods, the methodology, the techniques that we use to detect exoplanets. In particular, the techniques that I believe are going to push us forward to really build up the population of exo-Earths orbiting the nearest stars. And so now I want to continue this kind of broad introduction before we go into some of the challenges that we face when trying to increase this population of exo-Earths. And we're going to look at things like the mass function. I'm going to give just an introduction of the mass function and how that compares to what we expected from population synthesis models, or at least what population synthesis models compare, how they compare to the observed distributions. And as I said, then finally we'll look at where the field's kind of going, at least as an observational astronomer. So the topics from today, I said that this field has really exploded since 1995, since the discovery of 51 Pegasi b. It's really grown almost exponentially, and it doesn't seem to be stopping. And so the question is, what have we learned in those 20 years? So we started yesterday by looking at, or one of the things I said was that we've been trying to look at how rare or how common our solar system is. And so I want to look at a little bit what the response to that question would be in some level. And so we're going to look at what we've kind of learned from radio velocity analyses over this past 20 years, looking at the orbital distribution, the mass function, etc. over a few slides. Then I would like to highlight for anyone that's not really aware of the role that metallicity plays in sculpting planetary systems at some level. So looking at, as an observational astronomer, what we can study of the star and a connection to the stellar envelope and the presence of planets. And I'm going to say that this has been one of the key observables that we've found over the past 20 years. Essentially, it was one of the observables that really pinned down core accretion as being the formation mechanism compared to fragmentation of the disk. And you're going to hear a lot more about that in detail by Fred this afternoon. And so, finally, one of the things are what are we learning from radio velocities, from transit surveys? What have we learned, and how can we take that forward in the future to look at the smaller planets, the population of small planets? So maybe you're aware, maybe you're not aware, but I want to start on the stellar main sequence. And the reason I say this, I want to start there, is because we also work further up the main sequence. We work on more evolved stars, giant star populations, not only searching for planets around Sun-like stars, dwarfs, or small M dwarfs, but we're also looking for planets around G and K giants up the main sequence. And I'll show a few of the things we found over the past 5 to 10 years. And so for anyone that's not an astronomer in here, the biologists or so, when I say I'm starting on the main sequence, what I mean by that is, at least in this case, for the first set of 10, 15 slides, I'm looking at the Sun-like stars. And this is an HR diagram, arguably one of the most famous plots, one of the most important plots in stellar astrophysics, where we have temperature on the x-axis against absolute magnitude, or luminosity, if we like, of the star. And so the sun's plonked somewhere in here. We class it as a G2 star, so it's a G dwarf. And so for the next half an hour, 20 minutes, half an hour, I'm going to be focused on this area, focused on sun-like dwarfs. And so, let's get started. A real important distribution that we wanted to characterise really early, and this was done very well by the Keck survey in particular, who have, the Keck, remember, this is a 10 metre telescope on Hawaii that started one of the first exoplanet surveys, remember, using the iodine cell method that I explained yesterday. So this is not the simultaneous thorium method, this is where we have the iodine cell in the beam, and taking advantage of that big aperture telescope. So this is a nice paper by Paul Butler, 2006, who took the sample, the Keck sample, that had substantial number of data points, and looked at the mass function, or the mass distribution, if you like. And this is what we found. So when I say mass function, I'm just talking about the number density of planets as a function of planetary mass. And what we found is, okay, well, it depends on binning here, but we get something that's proportional to mass to the minus 1. 1 over mass, essentially. That's what we tend to find. We tend to see that there's not too many planets up here in this kind of super Jupiter regime. So it seems, at least in the inner disk, I say inner disk, at least close to the star. We're not talking about disks in this. When we're talking about formation we are, but remember, we're studying old stars. We're studying stars that are not active, they're not young, such that we can really detect these planets. We can keep that noise down. So what we see are a deficit of really super Jupiters, if we want to call them that. And then there's a quick rise at a few Jupiter masses. So we seem to be able to form these things in quite an abundance close to the star. And the great thing for us is this real kind of power law shooting up at low masses. Particularly if we want to then continue on and look for the small planet population. It seems that if we invoke core accretion as a formation scenario, then core accretion can form small planets in abundance. And I just wanted to show something a bit more updated. We also looked at this just a few years ago, and we still see something that looks very similar, except now we could probe a bit more the low mass population. So in this case, we also find something that's a bit more closer to m to the minus 1 rather than m to the minus 1.1. But what we see here is there's also some kind of turnover at low masses. So there's a peak in this power law. However, I want to say that, of course, this is still difficult to constrain the sensitivity bias here. So this is somewhat of a heterogeneous sample in the sense that we removed young stars. We tried to deal with old stars, mainly just from Keck and the HARP survey. So 2 big surveys that have quite excellent completeness out to long periods. However, there is an incompleteness factor here. The interesting point is, though, that peak turns out to be something around 6 to 10 Earth masses or so, which is this kind of banded around canonical boundary for runaway gas accretion onto a forming core. So that may be something interesting, or it may not. It may just be that there's a completeness bias, and we're kind of working on this to try and get those statistics to work in our favour now. But again, it's just to confirm that now, even pushing towards lower masses, we're getting to a point where we believe, at least if we are complete in this region, that we're still increasing. The mass function's still increasing. So there seems to be a plethora of small planets around nearby stars. However, there's also other features in the mass function, in the sense that if we look back here, we believe that we're relatively complete in this region, and we've got a small deviation potentially from this power law. And what does that suggest? Well, do we need to move away from a power law? Is it two power laws? Is it what's the distributional functional form? And so there's a lot of work going on now to try and look at other functional forms that deal better with or to fit the mass function. And of course, being that we work in statistics, we want to keep the models as simple as possible. And something that's as simple as a power law can be an exponential function. And we looked at an exponential function simply raised to m sin I. Remember from yesterday, this is radial velocities, it's m sin I, it's not absolute mass. So there's some also a degeneracy of sin I in there, so it's the minimum mass we're talking about. But also remember that we're looking at populations now, so we're not dealing with individual systems. And we can see that even fitting an exponential function, there's potentially still some excess. And so, although an exponential function does better now than a power law, and I could have showed a power law fit here, it still has residuals that are off by 3 sigma from the fit. And so, possibly, we require, to fit the mass function properly, we need to be moving to maybe more than one model. And so, this is some work in progress that we need to try and better characterize the mass function. Because the mass function tells us a lot about how planets are formed. Arguably more than any other observational result that we've had, particularly by radial velocities. And so I quite like this kind of cartoon of planet formation in the sense that it makes things simplistic, and we see basically all the properties in one image, in the sense that we can see that we have big gas giants accreting gas forming. So these things have passed this 10 Earth mass boundary, or wherever we set that boundary to be, and they're accreting a lot of gas from the disk. In fact, if we look at the disk, it's set up to be something that looks like HL tau that we've seen yesterday. And of course we have all these small dust particles that are first accumulating to produce small rubble, and then we can create the 10 kilometer sized bodies that start to have gravitational fields strongly, and they can attract other bodies to create your kind of protoplanets. Of course, you heard yesterday, and you're going to hear again probably, that this part here, going from sticking these little dust particles to create the small rubble, is very difficult. Getting up to something like a metre or so, a few metres in size, is quite difficult. Yeah, that's one of the real issues we have, and it's a lot of research is going into that at the moment. And so I think this is going to be a fertile area, and we heard particularly yesterday, Alma is going to push a long way to try and help resolve these issues. So, from radial velocities, it's an indirect method, but we get mass. That's what we get. We get a minimum mass from the radial velocity. And so from that distribution, we then need to look at what do we predict from models, from theory. And so I just want to highlight here, so this is a prediction from population synthesis models by Mordecini, 2012. There's also a nice series of papers by Ida and Lin following along this track. So if I now forget about metallicity, we'll look at that, come back to this in a few slides and look at that when we discuss metallicity. But all I want to show you in this case is that, so we have what we're getting in a kind of first order broad look at theory or core accretion as a possible route to form exoplanets. We see that we get a bump, some population of gas giants, and broadly we predict also this increase towards low masses. So to some kind of first order, there's also predictions of bumps in a Neptune sample. So forming kind of Neptunes out in the disk, and then you get to the type 2 type migration. So migration of planets is thought to go in 3 forms, 2 particular forms that's been studied for a while. type 1 and type 2, where we have these small bodies that haven't opened gaps yet. They're not big enough to open gaps yet, and they migrate very fast in the disk. So they migrate through resonances in the disk, and they migrate very fast. And then they reach this critical core mass limit that I said, where 10 Earth masses or whatever we set that to be, and they open up a gap. You get all the accretion. There's no stable core envelope solution, so all the gas collapses onto the core, and then it migrates slowly. So it follows like the viscous flow of the disk, essentially. It's a much slower evolutionary state. And these things are kind of predicted to be the form, and they're not quite at the supercritical limit yet. They're in that boundary, and so they migrate. Although they're migrating slowly, they're accreting solids and stuff through the disk, and they predict that bump, which is trying to be studied at the moment by various groups. But whether that exists or not, we're going to see. Basically, there's a deficit predicted, a desert that actually was shown not to exist, particularly at short periods. But to first order, they predict a rise globally. So if we look at it globally, they predict a rise. Now, for theorists, of course, there's a bunch of limitations to this model, in the sense that they start. I just said that it's very difficult to produce the first small objects, and in these models are seeded. They're seeded by something like, I think it's 0.6 or a half Earth mass in that regime. So they're kind of forgetting about the first, let's say, million years or so, and they just seed and then evolve and see what happens. And they also don't care about collisions after. These things are running away independently. So there's some limitations that we need to remember, particularly for this regime, in the sub-10 Earth mass regime. This is quite, there's some, at least, limitations to what we get from this. But the good thing is that we predict an increase. So to first order, it's a good, we're doing well, just invoking core accretion.
James, the bump is in agreement with the previous plot, right?
We're going globally on this. Well, this part here is, what I mean is...
I mean the bump related to the access.
Right, well, this is at a different scale.
Oh, this is...
So we're down at 10 Earths here. Before we go back. We're talking. Sorry, we're talking in Jupiter. We're talking now in Jupiter masses. Yeah, so we're on a different scale.
Okay.
Yeah, I was looking at this in Earth masses since being in astrobiology. We want to look down here. This is where we're pushing towards now. So I just wanted to show some. Well, actually, this is propaganda of me, but. I wanted to show some observational morphologies, and I showed a few yesterday, so maybe this wasn't that important, but this was basically my excuse to show you one of the... We run a survey from Chile, based a metal-rich survey, and so this was my excuse to show you some nice plots of gas giant planets. But the important thing is that when we look at these gas, particularly the gas giant population through radial velocities, look at the morphologies here. I mean, coming back to the solar system, everything's essentially circular in eccentricity. It's all nice and stable and circular. These things tend to be, gas giants tend to cover quite a wide range in the distribution of eccentricity, and that's really interesting. We have quite a large population of what we've now dubbed as being eccentric gas giants. And so, I mean, look at this. This was published based on one data point from the Anglo-Australian telescope. Actually, before they got the referees report, they had another data point somewhere off here, so they confirmed. But this was fit by a completely different solution until that one data point was gone. So this is close to 0.92. It's actually 0.97 now, with updated data. So this is 0.97. I mean, we're right in the extreme tail end of the distribution here of eccentricity. And so this is just to highlight that these extreme systems exist as well. We're covering quite an expanse in eccentricity. Okay, so So one of the nice works, again coming from the Keck sample, was done, published in Cumming et al. 2008. And what's nice about this was probably the real first true effort to deal with the sensitivity issues, the biases in the radial velocity data. Because there's various biases. I mentioned a few yesterday talking about, well, we have problems with the window function. So cadence is a real issue. And we've got human reasons for that, for instance, in the sense that we need to publish papers. And so when we see a signal, that star is then put on a pedestal and it's hammered. And so we end up seeing that when we have large signals, or evidence for large signals, these stars end up with a much higher cadence than other stars that are basically what we're going to call flat noise stars, at least when we think about planets. So in the Cumming paper, they really tried, they really looked into the biases in detail and looked at sensitivities. It was one of the first real works to do it. And this is what, when we look in period, we see. So the cumulative fraction, we get this kind of big rise out here. Of course, we're still talking about the gas giant population now. Only a few small planets were included in this analysis. But we see a few things. We see evidence for a statistical peak at short periods. This is kind of the hot Jupiter regime. So I mentioned yesterday that hot Jupiters, they're quite dynamically important, I say, or at least they're rare in the sense that they're only about 1% of Sun-like stars have these things. So it's interesting to understand how they form. How did they get there in the first place, and why are they there? Was there more of them? Have they been photo-evaporated, or what? I mean, they're really quite interesting systems. And so we see, if we look in period, and we try to deal with these biases, we get a little bump here about 3 days, then a valley, and then we get basically what we call the core population of gas giant planets out here. That's what we see beyond 100 days. It comes up, and we see all of these gas giant planets out at longer periods. And so here's what this paper tried to do. This is what I want to highlight. So looking at period against mass now. So we take the minimum mass and look at it as a function of period and see where these planets arise. And these blue lines represent the confidence limits, if you like. So this is one of the key points, that really looking at the sample and trying to deal as best you can in some kind of statistical way with the biases, with the sensitivities. And I'll show some more works now where we're doing this, pushing it to really lower masses, mainly around M dwarfs, where we can do this. We also highlight the radial velocity limits. So we've got 3 meters per second, 10, 30. Remember, this is 2008. We're going back Keck data from the early 90s. So the first real survey to start at this limit was the Anglo-Australian Planet Search in the mid-90s. That started with 3 meters per second because their core science goal was to find the population of Jupiters, real Jupiters. So things out there at 12-year orbital periods, and you need 3 meters per second from the beginning to do that. So you can see that the detections here that we've got, and some that are less confident, shown. We've got these green simulated things and observations. The detections are all above this 3 meter per second limit. Keck at the moment now is much more stable. I say much more stable. It's at least 1 meter per second or 2 stable. 1.5, 2 meters per second. But because of the legacy value of this going back, it was a 3 meter per second, beyond a 3 meter per second survey. And so you can see you're only at 5% confidence down here. You're 100% confidence up here, which is the Jupiter regime. So they're real confidence in their analysis of Jupiter type planets. But then we become less confident, even getting down into the signals that are at the 3 meter per second level or so. And here's some of the numbers. I don't really need to go through much of this. You've got kind of fractions of planets, a function of mass, but this is more for you to take away if you want to take a look at some of the numbers as a function of period. It's an interesting table to look at. And so we've started to look at this again more recently. In particular, as I keep saying, now that we can push down into the super-Earth, kind of pushing towards the Earth regime. And this is what we start to see now. So again, this was highlighted to be metallicity. We can kind of forget this now and maybe look here at eccentricity. But we see this is the gas giant population, the eccentric gas giants that I mentioned. These big dots are really just from the paper. They were detections from the paper to make them stand out. There's nothing special about these at all. But this is what the distribution looks like. As I said, you've got this, in this range of black to red, you can see that the kind of gas giant population, okay, it's quite low in eccentricity for the bulk. Most of them are below about 0.5. They're in the 0.4 or so eccentricity regime. But there of course, are still these real eccentric objects. They exist. When we start looking down at the kind of moving towards the Saturns, the Neptunes, and the super-Earths, these small things start to look more circular in their orbits. They don't seem to be producing, we don't seem to be at least detecting many highly eccentric small planets. And whether that means they don't exist, I'm not going to make that claim at all, because there is a hell of a lot of bias here. We're biased against the detection of them, particularly using things like the Lomskargo method that I mentioned yesterday. We've got a bias against that straight off. But it tends to be that we're finding more circular orbits for the small planets. And particularly, maybe some of the also bias in this plot is that I've now introduced a few M-dwarfs to this. And I showed you yesterday these M-dwarf systems like GJ667c, where we have all of these planets, and Kepler are finding these as well, where we see all of these planets that are essentially dynamically packed in space. They're all just sitting there and really close to the star, really small. And so they're nice and dynamically stable on nice circular orbits. And that may be, we may be seeing a bit of a bias because it's small stars. That's what the small star population starts to look like. At least for small planets, anyway. So, continuing with the population synthesis results, where now we're again looking at period, semi-major axis in this case, against Earth mass. And one of the predictions, kind of down here, that came out of this population synthesis, remember core accretion modelling for planet formation, was that there was a predicted Neptune mass desert on short periods. And it was a strong result in the case that it was predicted by the Ida and Lin in 2004, but it was also confirmed, let's call it confirmed, or at least in agreement with these models by Mordesini et al. They also found a deficit on short periods. You get this kind of boundary, that's a numerical effect, and then there's this deficit. And so the question is, does that hold up to observation? And it turns out it didn't. So although I'm showing these nice models, this nice population synthesis, this is where we are now, things are looking good to first order, we're getting increasing fractions in mass, for instance, to small masses, like we see observationally. There's a few details in here that don't add up, let's say. And so this was a paper by Andrew Howard in 2012, which kind of took its Kepler data and Keck data, where we could try and get essentially, well, first of all, looking at Kepler data, Kepler data as a function of period, and looking at occurrence rates, and binning those up into different radii. So going from the kind of small things here, couple of Earth radii, down to these kind of more big planets. So this is binned up to 8, from 8 to 32, 10 to 32 Earth radii, just to work on the statistics. And it turns out when you look in this regime in here, that was predicted to be, if these are classical Neptunes, if that's what we want to call them, 4, 5, 6, whatever Earth radii or so, then it turns out actually there's quite an abundance of them. There was no desert found. And this just shows it in the cumulative fraction if you want to take a look at this after. So, although it was there was a prediction of a Neptune desert on short periods, it didn't seem to hold up, didn't stack up to observation when it was analysed with Kepler data. And I'm going to discuss a little bit about Kepler, but there'll be a focused talk on Kepler this afternoon, so on small planets, so I'm going to try and keep away from it. Okay, so I mentioned that metallicity seems to be important. It's maybe a tuning parameter, if we want to call it, for planet formation. Tuning parameter, or at least a signpost of planet formation. And so let's go ahead and look at what I mean by that. Why is it important? Well, first of all, for anyone that doesn't know how this is done, here's how we extract the metallicity of stars like the Sun, essentially. We do it in two ways. The first way I'm going to show you was done in a paper we did with Yakiv Pavlenko. I did one in 08, but a bit quicker, a bit nastier in reality. And then we developed a better method using spectral synthesis fitting with Yakiv Pavlenko in the Ukraine, where essentially when I'm talking about metallicity, I'm parameterizing that by iron. So when I say metallicity, I'm basically meaning iron abundance. And so what we do is we take, and this is a nice example of a stellar spectrum in black, HD 1835, where of course we've got wavelength in angstroms against just normalized flux. And we see, then we try to model it using a model developed by Yakiv Pavlenko, a radiative transfer model. We try to build up a model of synthetically the spectrum, which has some benefits beyond. I'll show. We also do it using just equivalent width measurements of the lines, or just integrating the area of the line, if you like. But there's some benefits to using this spectral synthesis, and it deals with things like blends a bit better. And so we can take into consideration rotation and things like that. And these are the types of results that you get when you do that. Not only, of course, I say metallicity, I talk about iron, but we also, because we're modelling the spectrum, and because other elements are interesting, we also, of course, look at other elements, some heavier elements that I show here. And this is just a comparison to basically allow you to believe me that we do quite a good job. We've got fairly, let's call them accurate in the sense that they agree with previous works, and they're pretty precise. Show here log of the iron abundance against VT, against microturbulence, which is another broadening function that we need, kind of ad hoc parameter to get equivalent widths and stuff to match. And this is the kind of contours we get. So 1, 2, and 3 sigma. And these are the values. This was that star I showed before. And when we plonk it in and compare to previous results. So this is interesting for if you want to look at the population, the abundance of stars, population. A lot of work goes into this, beyond exoplanets, just in case anyone's interested. And I say that, there's interest in secondary science, chemical abundances, things like that. I'll leave this if you want to take a look. However, we also, to increase confidence in our results, and also to allow it to be more, let's say, efficient, and do this in a fully automated fashion, we've just developed a new code that does this using equivalent width measurements, so just integrating basically the individual lines. Trying to select lines that are essentially not blended, etc., and doing just void profile fits and trying to integrate the line, calculate the equivalent widths. And this is some results that one of my grad students, Maritza Soto, is going to work on, going to publish. She just developed this code, it does this automatically. And again, I'm just showing the distributions here. We determine bulk parameters first: mass, age, temperature of the sample, and then from this we can get a robust, self-consistent, kind of homogeneous measurement of the metallicity, which is the iron abundance. And things like log G, and again this microturbulence parameter. But this is just to convince you that, to show how we go about calculating these metallicities and chemical abundances, and I'm now going to say why this is important. I'll pass by that. That's just to show that we're also including about 12 other abundances in this. But here's why this is important. And this is maybe everyone's seen this plot. This is one of the famous plots that's came out of the radial velocity analysis. One thing to note, actually, before I discuss it, this result was kind of found in 1997. So when there was only 3 planets discovered at that time, it was an interesting point made by Guillermo Gonzalez, who just said, well, they're all around super metal-rich stars. Is there a reason for that? Do we need super metal-rich stars to form big gas giant planets? And subsequent analysis, Fisher and Valenti and the Hart survey, Sousa, etc., started to find, well, when we look at the abundance of iron in the atmosphere of sun-like stars and compare that to the sun, so we set the sun essentially to 0, that sets the 0 point on this scale, and we look at the percentage of stars with planets, because at this time there was still a discussion, are these atmospheres metal-rich because they're polluted by the disk, or accreting the disk, or by engulfment of planets or so? Or is it really that when we look at it, there's a functional form, a smooth functional form that tells us that this is through formation, there's a formation mechanism that drives this? And it turns out that's the case, that when we look at that, when we look in the highest metallicity bins, we see basically this power law function where the probability goes as the number of iron atoms squared. It's raised to the power 2. So it's a strong rising function with metallicity. And of course, if we need to think about the population then, because the galactic population of sun-like stars, function of metallicity, peaks somewhere about here, and it's kind of Gaussian. It's a kind of Gaussian function, so there's not many stars in this bin, but if you can find them, or you study them, you're going to find many big planets. Big planets, remember. This was done down to about 0.4, 0.5 Jupiter masses or so. So we're still talking about gas giants here, and that's important because things may be turning around now that we're looking at the small planets. This bias that exists for gas giants may not be the same case when we start looking at small planets. So you can see the sample is nothing like what I just showed binned up for the gas giants. But when we looked at this a couple of years ago, so this is the same plot, it's metallicity, except now we're just looking in M sin I. I mean, it was pretty difficult to make bins out of this. But one of the interesting points that came out of this was we see these sub 0.02 Jupiter mass planets. So this is Neptune. These are all Neptunes. So this was just sub-Neptune mass, minimum mass. This is the core accretion boundary, this runaway gas accretion, roughly. But if we look down to this kind of sub 0.02 Jupiter mass regime, we tend to find there's quite a few planets here compared to the sample. And the area my survey was interested in, there was essentially none here back in 2013. And this doesn't go all the way up to 0.5, and there's very little stars in this regime. But we don't really see anything in here. And if you make this very crude, of course, cut, and start looking at it statistically, doing a Monte Carlo or a bootstrap analysis, this gap here was significant at about 4.5 sigma. But of course, this was me in my bedroom just making a slice along here and saying, right, is that statistically significant? And I mean, there's maybe nothing that really defines that limit, but maybe there is. Maybe what's happening is, at least in the bulk population, you're having these small planets, and there's so much dust, there's so much metals in the disk, that these things rapidly reach the critical core mass limit, wherever that is, and then shoot up to become the gas giants. So it could be just that maybe there's this is another validation of core accretion at some level, that in the super metal rich regime, there's just no small planets because there's so much dust, they form so fast that they rapidly evolve into gas giants, possibly. Now we'll see with bigger samples if that could be the case. Well, it seems, at least some works from Buchavi et al. Quite recently, looking at Kepler data. Remember, the Kepler stars generally, they're fainter. I've just shown how we calculate abundances, how we calculate metallicity. These stars, it's much more difficult to calculate metallicities from them. It's harder to get really super high signal to noise, really super high resolution spectra to do these calculations. But when you can get a sample and do it, you start to see that maybe also the stars with planets, shown here, are kind of maybe moving down. This are stars with small planets now. So this is still down in this kind of small planet regime, the sub-Neptunes. And when you do that, based on radii this time, so I looked at it based on minimum mass, this is based on radii, then you start to see the population kind of follows the distributional population. It peaks down here at below the defined boundary of where the sun is, the 0. So potentially this is an agreement where small planets tend to form more around metal poor stars. However, there was just some work a month ago or so, maybe a couple of months ago, by Mulders et al., who threw maybe a spanner in the works in this kind of idea of what this could mean, in the sense that when you look at orbital period against metallicity for different planetary radii, in this case, when you get down to the smallest planets, 0 to 1.7, so this is probably the kind of rocky regime. These are in the rocky, they're all mostly rocky planets. When we do that, they argue for an increase in metallicity, at least at short periods. So if you bin up in radius and planetary radius, etc., you bin up and you compare, this is delta metallicity now, so taking essentially the population, that's the population mean, and this is just a kernel, a moving kernel, so you're looking at kind of binning this sample up and looking at it in metallicity and looking at delta metallicity. They're arguing for, at least certainly at short periods, then it looks like the Rockies are more metal rich, they're biased towards metal rich stars, compared to the slightly bigger planets, the super Earths and beyond. So they're making the case that actually if you look at short periods, no, the small planets are orbiting very similar to the super gas giants. They orbit around the most metal rich stars. And so this needs a lot more work, and we need to build the sample, and it needs to be done on nearby stars. It needs to be done where we can really get the spectra to do this, to do the analysis to high precision. And so we can look at the planetary mass function as well as a function of metallicity in this regime, and try to see, does the mass function, the minimum mass function, change as a function of metallicity? Given that I've just said that it maybe does when you get down to the real low mass planets. However, when you do that, you may see something against the real metal poor and the kind of super metal rich, if you compare them, at really high masses. There may be actually a higher, this argues for a higher fraction around sun solar metallicity stars. Now, I'm in no way going to claim this is anything here. I would say that actually these are fairly similar. And if you run statistical techniques, Monte Carlo or whatever, then you turn out this is pretty standard. They're in pretty much agreement. So it's kind of inconclusive if there's any change in the mass function as a function of metallicity. But this is work in progress.
Which sample is this?
So this good point, in the sense that this sample is the same sample I showed before when we looked at the period eccentricity mass plane. So this sample is generally consisting of 3 samples, and it consists of Harp's, Keck, and my CHEP survey, which is Harp's. So CHEP's and Harp's basically are the same survey, except CHEP's is biased. So you have to take out that bias, which I did a little. We're going to really work on. We have a paper coming out next year where we're really going to try and convolve these samples, particularly Harp's and CHEP's. We're analysing the metallicities homogeneously and getting rid of all the sensitivity biases. So we'll be able to really look at these things next year in a much better, much tighter statistical way. But then we can come back to this mass function plot and look at the mass function as a function of metallicity from the population synthesis models. And we see again the first order broad agreement. What we see observationally. We see, if we look at the core population of gas giants, we see that in the metal poor regime, so the red, the most metal poor, blue is the kind of intermediate population spanning minus 0.1, remember this is in log space, minus 0.1 across the solar regime to, that's super metal rich. Above 0.1, 0.2 is super metal rich, but this is kind of going into the super metal, and then you've got the most metal rich stars. Remember, this would be the population minimum in the sense that there's many less stars in the distribution here, but when you do that, you recover exactly what we see. We see the rise to higher fraction of gas giants in the metal-rich regime, or the higher fraction of Jupiters at least. And then when you come down, we see a turnover. So the core accretion in this paradigm actually predicts that small planets should orbit kind of sun-like or more solar metallicity or less type stars. It's predicted. So we're looking at this area where I showed, Bochavi showed that potentially there's a change, and some others before us had suggested this as well. The Harps people, Udry et al, with just a few detections. And then Mulder sees this increase at least at short period. However, and then prediction says, well, actually, core accretion says if we look at it population synthesis way, and we look at the population in general, it says that, yeah, there should be a decrease at high metallicity. There should be a lower fraction of very small planets. Now, we do need to look at this in the sense that it's predicted in this regime, and that's really where we've been looking, the sub-Neptunes. Because, as I said, this is kind of underpopulated. And even in this, remember, even in this theory, even in this model, remember I said that the seed is about 0.6 Earth masses. They forget about things that happened before the first million or so years, and just seed it at 0.6 and they're individual planets, not multi-planets, and they forget about collisions and things like that. So sub-10 Earth masses is, this is hand-wavy, this is broad. But it may be agreeing with what we're seeing. And we'll find out more over the next 5 to 10 years on this. It'll be a lot of study. And we can also look at the fraction with orbital period as well. So we want to see if the planets that are close to the star are drawn from the same distribution as the planets a bit further away, because then we're probing migration. So we probe migration effects at some level. And when we do that, we can see that, so remember in the coming paper, at 100 days or so, that's when the gas giant distribution started to increase, the fraction started to increase. So if we look at periods below 100 days and above, so in mass, one thing we see is, so we can split masses into 0.1 Jupiters or so. So 0.1 Jupiters, at least for hot Jupiters, we say, it's kind of again a bit hand-wavy, but we define a hot Jupiter, we define it as being something like mass bigger than 0.1 or so and a period less than 10 days. So 0.1 is kind of hand-wavy cut-off for a gas giant, let's call it that. And when you do that and you look at metallicity, number one, right, we recover that kind of expectation, where the most massive planets are towards high metallicities. And then you go on and say, okay, what about period? And so we split it in period and say, okay, let's cut below 100 days and above 100 days. And number one, that gives us a statistical population. And I say a statistical population, we're looking at 2 bins here. So it's not quite a statistical population, but it means at least each of these bins that we're looking in this kind of subsample of 2 has enough counts in there that we can say it's statistically significant. And when we do that, you can see that the planets close to their stars, the planets that are on periods shorter than 100 days or so, may have a bias towards high metallicity. And if you run an Anderson-Darling test or so, then it turns out you get a probability that is statistically significant. So this is arguing that potentially there's a change in the distribution between nearby planets and further out planets. I say a change in the distribution, it may mean that there's a correlation with metallicity. So metallicity plays some kind of significant role in migrating planets. Now whether that's because there's a higher disk surface density and you get a stronger interaction at the resonance sites and so you migrate more, that may kind of make sense in this paradigm, given this result. But that's a hypothesis to be tested. So, another interesting result, moving away from just metallicity and now looking at some lighter elements, in this case, so not iron, looking at lithium. And this was a result published by Israeli a few years ago, updated, but this was published a few years back, where they looked at lithium as a function of stellar type or temperature. So the abundance of lithium is a function of spectral type, if you like. And what they found was that the stars with planets in red tend to have a bit of a lower abundance than the mean or the population. So, and it's statistically significant, lower abundance of lithium. Now, and lithium's easily, quickly destroyed, or light elements are quickly destroyed in stellar atmospheres. So the question was why that was the case. There may be and there may not be beryllium. I just want to show this as work, we can skip by that. But potentially what we've got going on here is that when you have planets, particularly big planets, we're still in the big planet regime, that may have, the theory was, or the idea is that we form planets, big planets, in longer lived disks, slightly longer lived disks. And those disks can break the stars for a longer period of time. And what you get then is a higher shearing inside the atmosphere, and so you can destroy lithium at a much higher rate than without that disk breaking, or at least the longevity of that disk breaking. And so this was an idea put forward. I say an idea. It was Jérôme Bouvier published this theory of disk breaking and having longer-lived disks breaking the star. And so you can look at that and say, okay, well in the upper envelope in this convective, we've got differential rotation and things going on. That if we get that increased breaking, then we can destroy lithium at a higher rate. And now we've got a theory that would actually predicts the destruction of lithium, and predicted that under abundance that we observed. So since I've only got half an hour and I'm like halfway through, I'll skip some basic things. And now let's move up the HR diagram and see what we find. So I said that we've been looking at the sunlight population. What about stars that are more evolved? What about these things that were a bit more massive on the main sequence, like the A stars and stuff, and they've evolved across? They're now cool enough that they've got a lot of lines in their spectrum. So we can't, by radial velocities, we can't find planets, and I'll mention this tomorrow, we can't really find planets around hot stars, just because there's none of these nice iron lines. It's not blanketed by any lines to use to actually measure precise radial velocities. So we wait until they evolve across onto become giants, and they've spun down as well, so they're nice slowly rotating objects, and then we can see enough lines that we can actually measure radial velocities. And so what we find is actually they've got quite a high occurrence rate of at least of giant planets. Now remember the bias in radial velocities. The problem is it's hard to detect small planets around these big stars because they're more massive. And also they turn out to be more active. We'll see that tomorrow. They turn out to be more active. It's harder to measure precise radial velocities. So they're active at 10, 20 meters per second level. But that allows you to look for big planets, giant planets. And so what we see here is that these things are quite abundant in giant planets. And also we seem to find that we have a nice fraction of them, like I said, 10% or so here at 2 solar masses. But then you get this kind of drop. We see nothing essentially above, let's say, certainly at 2.9 solar mass. When you get close to the 3 solar mass limit, of course, we've not got many stars, at least in our sample, but this is confirmed by other works. When you get into this regime, we're not finding anything. The fraction's essentially 0. And if we look at it in metallicity to compare with the FGK sample, the dwarfs, if we do that, we also find this rising power law. So when we deal with those statistical biases that we discussed earlier, we tend to find that the fraction with metallicity goes as something like, well, the abundance to the 1.3, something like that. This has got a big error bar. It actually agrees with f to the squared. It agrees with the dwarf sample, to be honest. But the point is that it turns out there's a statistically significant increase in metallicity. And this is just to confirm that other works see the same result. That when we look in metallicity, we can look in specific regimes, and we find this increase with high metallicity. It tends to be flat at lower metallicity, and also lower mass giants have a higher fraction of planets at lower metallicities than higher mass object giants. So you see this increase coming down in stellar mass from 0 to 12, and that's across the entire board, actually. So what we can do then is we can look, if we've got a sample of, let's call them retired, or they were called retired A stars in Johnson et al. Work, 2010. We look at the FGK dwarfs, and now we're also starting to pull in the M dwarfs. So this is from Keck. This was done from Keck and Lick, and so we're looking at stellar mass against metallicity, and we get where these are the means of this kind of running means of the sample, and the blacks for planets, and the blacks are just the full sample. And we tend to see that there's an increase in all of these bins. Now, I want to say the M dwarfs here, it's difficult to generate precise metallicities of M dwarfs. Their spectrum, particularly in the optical, is blanketed by TiO molecules, and it's quite nasty to try and model. But when you try and convolve those three different regimes, what you find is that the giant fraction falls off linearly with stellar mass. So you can look here and say that at least for giant planets, this is giant planets, the giant, let's call them giant stars, have a higher fraction of these guys, and it kind of drops down as you come down in stellar mass linearly. And you recover the metallicity bias as well. But the point here is, high mass stars are rich in planets, maybe because they've got much more massive disks. If we believe there's a correlation that appears between stellar mass and disk mass, and how we characterise disk mass, I guess, is another issue, in dust and gas, etc. Then if we believe that correlation exists, this could be telling us that these things are rich in big planets because the disks are big, there's more stuff there to form them, and it fits in with metallicity. Maybe the disks are fragmenting, but we're talking again still about these things being close to the star. So I introduced M dwarfs in this sense. Now we'll take a quick look over a few slides at M dwarfs, because M dwarfs are, at the moment, they're our way to search for small planets in the habitable zones of stars. So if we want to talk about, and I say stars, I mean nearby stars. If we want to talk about the quick route in this astrobiology meeting to building up the population of exo-Earths, then M dwarfs are our quick route in the nearby future to do that on the nearest stars. And we heard yesterday, we talked about the fact that they're the most abundant stars. Of course they're fainter because they're smaller, but now we're getting efficient enough that we can draw samples. And draw samples at a mere per second or so, radial velocity precision. And when we do that, what we find is if we look at the detection fraction orbiting small stars, and this is work we did with Mikko Tuomi, and we look at period against mass and Earth masses, where the shading we've got is our completeness. So remember, yesterday I talked about doing MCMC chain tempering, etc. Well, if you do that, and do it properly, then you automatically can, well, quite simply look at your probability as a function of period. You can deal with your sensitivity bias just by analysing your chain straight off. You're, even beyond it, you're injecting fake signals and stuff. So if you do this by Lomscargo periodogram analysis, what you have to do is inject signals into your data at varying periods and with varying phases and amplitudes and stuff, and that's how we build up the statistics. That's how to deal with the completeness. That's how the Cumming paper did it. If you do MCMC analysis, you get that for free if you do it properly with your chain. You can analyse different periods and look at your probabilities straight off. And so when we did that, what we saw is kind of shown here, represented by what we see, where we show these blue objects that were detected planets previously. Then we show our detections are in red. These are our M dwarf detections. So that was new at the time when we did this paper. And these things with circles are, all of them are what we call SRCs. They're things that are possibly planets. They're just not quite at the probability threshold yet. So they could be planets. And when we look at that, we tend to find that basically 100% of M dwarfs have planets in this period bin between 10 and 100 days. 100%. Every M dwarf has a small planet. Every one of them. And Kepler finds the same result here. Dressing and Charbonneau analysed this and found the same result. In fact, they found that actually the fraction something like 2 or so per star. And we have an updated paper that will hopefully be out by the end of the year that agrees with them, 2.2 or so objects per M dwarf. So every M dwarf has planets. You go up in mass, 10 to 30 Earths, minimum mass, remember, then it turns out only about 5% or so, 6% tend to have in this period band of big planets. So M dwarfs are rich in small planets, but they're not very rich in big planets. In fact, there's only a handful of Jupiters around M dwarfs, nearby M dwarfs. So those things are quite prized objects. If you can find wide orbiting Jupiters around M dwarfs, they're really prized orbits for instance, direct detections, follow-ups, which we're trying to do. One of the important points to highlight is the habitable zone when we did this work. And we've got new statistics coming out on this, but it tends to be roughly the same. But we have somewhere in about 20% or so of M dwarfs have 3 to 10 Earth mass planets in the habitable zone. So the habitable zone of M dwarfs is rich in planets. And remember I showed yesterday that, like for instance, 667c, JJ667c had 2, possibly 3 in its habitable zone. These things are all dynamically packed, or at least packed in some respect. Then M dwarfs have a strong probability of at least a few systems, I say a handful observationally, that will have multiple planets in the habitable zone. Comes back to how we define the habitable zone. But now we try to go to late M dwarfs, so now we're even fainter stars, much fainter stars. So this is right now down to the 80 Jupiter mass limit and 90 Jupiter mass, right down to the limit of stars, going from the boundary of stars and substellar objects. And we try to observe those as well with radio velocities, and they're damn hard to get a statistical population. But we did it on UVs in particular, on the VLT. We could observe these with UVs. And what we found, sadly, I say sadly, this remember we're going down in mass, so for a given planetary mass, the amplitude and radial velocity is going to increase for a given period as well, period in planetary mass. The problem was that we found that all of them had RV scatter about the 10 meter per second limit. So this is what we show as log of the radial velocity on a log scale against, in this case, V sin I, M spectral type, and the flux in the H alpha line. I'm going to discuss these things tomorrow when we look at the difficulties in actually detecting exo-Earths. But if we look at the M spectral type, what we see is here's this big line is marks 10 meters per second, and what we see is that once we get down to the kind of latest M spectral types, the kind of coolest stars that exist, then essentially everything has an RV above 10 meters per second. So the question is it activity? So is it real? From just real, when I say real, is it from the start? Or is it Doppler? I mean, is this scatter because they're rich in planets as well? Well, actually we'll see that it probably is activity. And one of the reasons it might be activity is also, I say activity as I'm including rotation in there, is also that when we analyse, we try to build a sample of M dwarfs as a function of spectral type. What we want, one of the things we wanted, at least when we looked at this at Penn State for the precision radial velocity spectrograph sample, we decided, well, one of the cuts we want to make is rotation. We want slowly rotating objects, and I'll explain why in a bit more detail tomorrow. That what we found is actually the partially radiative stars, so the early M dwarfs, are quite flat. Their rotational velocity distribution tends to be quite flat, and it's low. It's a few kilometers per second. And then you look at things towards after the kind of canonical fully convective boundary, somewhere in here, the M4, M5 regime. And if you look at those, the distribution of rotational velocity starts to increase. And so this is at least partially the reason for why we see these late M dwarfs with high radial velocity scatter. And we'll look at it tomorrow and see why. And so it looks like there's actually, maybe we can call for two distributions for the rotational distribution of M stars. Early M's are all peaked towards low v sin I, low rotational velocity, and the later M dwarfs are actually have a much more of a broad distribution in this sense, towards higher v sin I anyway. Okay, so since I have like 10 or 15 minutes left, I wanted to look at some of the period, mass, radius and occurrence rates, and what we can learn from some individual systems, in the sense that what I mean by that is looking at density and bulk composition. And I know we're going to go through this, as I said earlier, in this afternoon, so I'm going to give a kind of broad view over this. What I wanted to show, starting with this, is the Kepler period radius distribution. So probably at the moment, observationally, one of the most important plots we can make is kind of the radius mass plot, in the sense that the radius mass plot allows us to look at bulk density for planets, and then we can apply compositional models and try to understand the constituents, at least the bulk constituents of those planets. So first we can look at radius, or period, in this case, against radius against period. And one thing to note is the kind of high fraction that Kepler sees in here, the Earths to the Neptunes, the super Earths. Well, we said that yesterday, that the solar system's got none of these. Actually, we were discussing this morning, maybe it has one, okay, this planet 9, but it'll be interesting to see what happens with that. But the solar system doesn't seem to have any of these super Earths, whereas Kepler finds them in real high abundance, real vast population of super Earths. Or it's got 91% of the detected planet candidates are smaller than Neptune in size. So that's the bulk composition, the bulk population, that Kepler sees. Note here, this is likely to be bias, selection bias. These things are hard to detect. The very small and very long period orbits. And these, for sunlight stars, this is where we want to be looking. This is, if we want these exo-Earths, this is what we need to populate. And you can also see the Jupiters up here. So there's big population, then there's still a wide abundance across period space. It's still well populated between Neptune and Jupiter. And then we've got the Jupiters as well. And one thing that should be mentioned about the Jupiters is there's been a recent paper that when it were followed up by Santerni early this year or just at the end of last year, they followed up the Jupiter population with the high precision spectrographs in the north called SOFE. And what they found was that about 50% of the things that the ones that they looked at turned out to be more like brown dwarfs or small stars. And remember I said yesterday that the radius distribution basically doesn't change from M dwarfs all the way down to Jupiter. So you need to remember that up here there's possibly a high contamination factor. So there may be a 50% contamination fraction of objects, at least in the Jupiter regime, the Jupiter radius regime. Down here we're a bit more secure. And we can look at this as a function of temperature of the planet, equilibrium temperature. One thing I just wanted to highlight here, since I'm running out of time, is there's a deep clustering of planets here. We're 500 to 1,000 or so Kelvin planets. And there's only a very small fraction detected in this kind of classical habitable zone. This is marked here by these lines. This is kind of the inner and outer boundaries, depending on what you believe the habitable zone is. But there's only a handful, at least at the time of this publication, that should be a bit more populated by now, and populated because there was a paper by Morton just this year that doubled the sample of confirmed exoplanets, up to over 1,000 or over 1,200, confirmed statistically. Remember, these don't have the bulk of these don't have radial velocities to confirm them properly or observationally, dynamically. But what you can do particularly, and this is just to highlight this, is we can use multi-planet systems to confirm them as planets. They have a much lower contamination factor, or so the false alarm rate is much lower if these things are in multiple systems, because you can apply dynamics. They can't be anything else, essentially. They can't be small things, white dwarfs or whatever you want to invoke here. Dynamically, they essentially have to be planets. In fact, the fraction they quote is something like 5% or less, kind of false alarm probability. So what I'm trying to get at here, beyond looking at the fact that this paper was about isolated hot Earths having a similar frequency to hot Jupiters, so did they have a similar similar population? Maybe they're the remnant population of hot Jupiters. But the point is that the contamination factor of multiple planet systems is much lower, so it's more reliable statistically. And just to finish up, we've discussed this a couple of times, particularly myself and Fred in the taxi. So I wanted to highlight some work by Jackie Faherty just this year. So she's been looking at basically how we can use brown dwarfs to characterise exoplanets, giant exoplanets. In particular, if we look in this colour space J-H colour, so this is a proxy for temperature, and we've got absolute J-band magnitude as your luminosity proxy. So this colour magnitude diagram in the near infrared, we see that compared to the field population, kind of shown in the background here, this is a field population. So these are all brown dwarfs, and where we see this kind of distribution of L dwarfs coming down here. So the L dwarfs are getting redder. They're dusty, they've got dust in their atmospheres, and then they turn over into the T dwarfs, so we get the presence of clouds coming in really here. And then down, if we say the late T's, Y's turn over again. And we get our planets down here. But if we look at the directly imaged planets, the young planets like HR8799, this is 3 of the HR8799s here. We've got AB Pic B somewhere in here. And Beta Pictoris B is right in the centre. When we do that, and we look at them, we see that in temperature, the young planets overlap quite nicely with a couple of populations. Well, there's a T dwarf population there, and the field population at that. But then they jut out a bit from the distribution in general. And they jut out, they agree quite well with low gravity dwarfs, particularly the low gravity L dwarfs. They've got similar temperatures, so similar colours. And what the idea here is that what you're getting is the effect of clouds. So you're getting extreme effect of clouds in these low gravity brown dwarfs. So what's happening is the spectral energy distribution is kind of changing. The low gravity L dwarfs, you're getting kind of depressed J-band flux, and that's being compensated by the flux in way out in the Wise bands, where they're a bit more brighter. So they're becoming really red. You're getting basically a redistribution of flux. I just wanted to highlight that if we're making the point of what planets are, particularly what young big planets are, and brown dwarfs or whatever. But it leads nicely into the mass-radius relationship, which I said is, at the moment, is one of the most prized observables we can get. If we can combine transits and radial velocities and really get observationally the mass radius of these individual objects, then we can look at composition models, and we can just plonk observations on this diagram and try and look at what the bulk composition of these are, the giant planets, the Neptunes, the Earths. This is showing them. So these are trying to basically, with their bootstrap from the Earth. That's what the equation of state is. And this one's actually, the paper from Seeger et al. 2007 was one of the first to do this, given the population of transiting planets that were coming from ground-based surveys. And so the point of this is that once we get these, we get the density, we can look at bulk compositions. Since this has moved on slightly, there's a paper just this year by Zheng et al. Who kind of uses an updated composition model. They use seismology of the Earth, essentially observations of the Earth, the interior of the Earth, to build up a more realistic equation of state of iron, etc. in the core, and a better mantle equation of state. And when they do that, this is what you end up with. This is their model. So we've got mass, radius regime here. And you can take these updated composition models, these bulk models, and apply them to observation. And this is what we see in the distribution for the time being. So planet mass against planet radius. And this was a paper we did with Nestor Espinosa at Católica in Chile. And what we were highlighting here is we found this from Kepler. This is K2. So I should say that Kepler, I'm sure it'll be mentioned later, it's kind of moved into its second phase now. So it's K2. We're able to look at more nearby systems than the K1 sample. And we found this planet that agrees on kind of identically, I want to say, but nice big error bars, with 100% rock composition model. So we've got something, we're seeing things with Neptune-like masses, and they could be formed purely by rock. Could be. At least that is agreeing with the latest models. But this gives you a nice view of the population. And there's other subpopulations in this that are quite interesting. You may have heard about super puffs, for instance. We're hearing where you're getting potentially things that are really low density and really nearby the star. They're kind of really puffy objects, and it's interesting to look at how they form. But all I want to say is to highlight that we're moving towards really populating the mass radius diagram, and we can use up-to-date composition models to try to understand the bulk composition.
Jim, before you go on,
Yep.
that plot was what we were talking about yesterday.
Mm-hmm.
Remember they asked you what's rocky and what's not, and what you were
Mm-hmm.
trying to say is right here, that if you look at to the left of 5 Earths,
Mm-hmm.
it's all along the rock line.
Exactly.
And when you get to 10 Earths, there's this huge diversity, right?
I actually had the plot.
Oh, okay.
But it could be done. Since I've got no time, that's a quicker way to say it. Yeah, exactly. This is the issue, that things fall along that rocky line, yeah, and then they explode beyond that, yeah. And it was highlighted here. This is a paper by Rogers 2015 that tries to give you the value for exactly what Fred just said there. That you can look at. I mean, this depends how we define what rocky is. It's dependent on the statistical model. But they make a hierarchical model, Bayesian model, to look at the probability of these things being rocky, and they come up with some value that this is the probability. And when you do that, you can see that things turn over somewhere about there. So there's actually nothing behind this plot. I just wanted to show you that the bigger sample is heterogeneous. So I wanted to make it clear that the big sample is heterogeneous. It uses TTVs, it uses ground-based RV detections, it uses ground-based transit detections, but this work by Rogers et al. It was more homogeneous. They just took away the TTVs, took away the ground-based stuff, and just focused on the Kepler sample. And when they did that, the Kepler sample that had fairly good measurements from Keck, radial velocities, that's why it's kind of small. When they did that, you get this kind of difference, this kind of offset or probability of being rocky that kind of shoots up once you're at 1.5 or so radii, Earth radii. And since I'm out of time, I'm just going to finish. I'll miss a couple of the slides. I just wanted to say that if we say that that's 1.5, 1.6 Earth radii, we can then look at some radius mass relationships observationally. It was done by Weiss and Marseille a couple of years back. And when you do that, you get something like whatever the value is, 5, 6, 7, 8 Earth masses, ballpark. You're in that regime for being rocky. So anything below that, 3, 2, we can say pretty definitively it's rocky. Anything above that has a higher probability of being gaseous, and probably is gaseous. These are updated occurrence rates. I think that'll be talked about actually this afternoon. So since I'm out of time, I'll leave it there and go to the summary. And so just to say that we've looked at the population distributions, both mainly from radio velocities that's driven the field until now where Kepler's really given us a sample to look at smaller planets. And we get agreement between observation and theory at some level, hand-wavy agreement. To first order, things are looking like, at least if we invoke core accretion, kind of looks like what we're seeing. We can look across different evolutionary states, and we're beginning to build up a picture. We're seeing occurrence rates change as a function of mass. We're seeing agreement in metallicity as a function of evolution, things like that. So we're beginning to really build up the picture of the exoplanet sample. And so, well, the idea here is to really move to the exo-Earth sample, or the real low mass sample. We really need mass now. It seems we've got a high population of radii from Kepler. We need to really start getting solid masses for these things, particularly, and we want to do it around nearby stars. If we could do it for Kepler stars, fine. We've got a lot of them, but we're going to have to do it around nearby stars. That's just, if we're using radio velocities, it's the way we get the signal to noise to do it. So I'll leave it there and take any questions.